Hi everyone, back for part 3 of our logistic regression series, running logistic regression with a single predictor. Here's where we'll bring in some new techniques. So the big difference for running logistic regression. With logistic regression, we're going to be using a command called GLM instead of LM. GLM stands for General Linear Model. It does a lot of different analyses, and we'll have to specify the sort of analysis we're after. You can see in the code, it's just predicting comply from physrec as we've done before, as we've done with regression a lot. We tell it the name of the data file is called Logistic II. Then we have to tell it the family of tests. The family of tests we're using is binomial, which just means that we're addressing dichotomous outcomes here. Going through what we have here, the estimate that we get, we see physrec, yes. And when we see physrec yes, we mean that it's being compared to no, so higher numbers would mean yes was associated with more of something. This estimate, that's very much like our regression coefficient. I'll talk about the estimate in more detail in a second, but you see we get an estimate, we get a standard error, and we get a z-value instead of a t-value here. Interpreted in the same way, if you got a probability of less than 0.05, it's statistically significant. We get a couple of other things. We have null deviance values and residual deviance. The null deviance is a measure of how well we're predicting the outcome compliance without any predictors in the model, and that's sometimes called an intercept-only model. The idea is that we can get a kind of a baseline of how good we could predict everybody, even if we didn't know anything about physician's recommendation. The residual deviance gets at how well we can predict once we've added that predictor variable, how well we're predicting once we've added physician's recommendation. Now, on their own, those two statistics aren't very useful, but where they are useful is when we compare them. We can actually take the null deviance minus the residual deviance, and this gives us a chi-square value. We could subtract the degrees of freedom from one another. That would be the degrees of freedom for the chi-square test. This gives us a test of whether the model is statistically significant. You would think after all these years I would be able to say statistical. This is analogous to the F model statistic that we get to test whether our R-square is significant in regression. So very similar statistics. We'll see that we get something called the AIC. The AIC is relatively popular in some fields. It's not useful on its own, but it is another thing that's used in comparing different models. We probably won't talk about that too much, but don't be surprised if you see it as a model comparison statistic in other places. The estimate, coming back to that, the estimate here is expressed as a log odds ratio. Remember, with a log odds ratio, okay, back to the log odds ratio. I noticed that there was an error on the slides, and I just took a second to fix those. With the log odds ratio, 0 reflects no effect at all. Positive values reflect a positive relationship. Negative values reflect a negative relationship. So this is telling us that there's a positive relationship between physician's recommendation and compliance. Both of the variables are coded 0 for no, 1 for yes. So as we have a larger value on physician's recommendation, which would mean that they have a yes, we tend to have larger values for compliance, more yeses. Now the log odds ratio, what's given here is statistically significant. We can see we have a p-value that's well below 0.05. But one of the issues with the log odds ratio here is that nobody really thinks in terms of logs. It's nice that it's got that symmetry with other estimates that we've seen, where a positive relationship is represented by a positive value, negative relationship is represented by a negative value, but other aspects of it aren't that useful. In particular, the piece where we're talking about log. So 2.29 log odds. What does that mean? It doesn't have the clear interpretation that we get from an odds ratio. For that reason, we tend to convert and report our estimates in terms of odds ratios rather than log odds ratios. And that's relatively easy to accomplish. The EXP function here, we just run that on our model, on the coefficients from our model. And we can see that we get a value of 9.86 now. What does that tell us? It tells us that people with doctor's recommendations are 9.86 times more likely to seek screening than those without them. So a pretty substantial difference there. One confusing thing about odds ratios, though, is that when we're talking about odds ratios, 1 means no relationship. So an odds ratio of 1 means that the odds for people with and without doctors' recommendations were exactly the same. That is, the recommendations didn't influence the relationship. Greater than 1 means positive, and less than 1 means negative, with this never being a positive or a negative value itself. So that's one piece in terms of the interpretation that we need to understand. Above 1 is a positive relationship, below 1 is a negative relationship. I also include the 95% confidence interval here. We might use that instead of a probability value to draw conclusions about the null. And here we would be asking not if 0 fell inside the interval, but if 1 fell inside that confidence interval. And here it clearly doesn't for physician's recommendation. We also get this information for the intercept, but I would just ignore that as we did with linear regression. All right, another type of statistic, one that's not particularly useful when we have a single predictor, but we'll talk about it in the context of a single predictor before we move on. In regression, we get an R-square for a model and an F for that model, testing the R-square significance. We'll talk at the end in the final set of slides about analogous statistics for the R-square. We'll see that that's a kind of a contentious issue within the logistic regression literature. But there is a clear analog to the F model statistic, and that is a chi-square statistic. That chi-square statistic comes from comparing the null deviance and residual deviance from our model. Then you can see mathematically, I've just kind of laid it out there. We're just subtracting one from the other in terms of both the chi-square and the degrees of freedom. And then we can calculate a probability from that chi-square thing, or if you're really old-fashioned, you can go to the back of a statistics book and look up what you need to reject the null at 0.05 for chi-square of 34.6 with 1 degree of freedom. The code down below here just pulls all of that information in and then calculates a probability for you. So you can use that without having to do any of the hand calculations here. You can see this gives us a chi-square of 34.6, probably is well under 0.001 even, telling us that our model does significantly predict compliance. That's not surprising. We only had one predictor in the model, and that predictor was statistically significant, but a useful statistic and one that people will generally be looking to be presented. Again, this is something that gets a lot more useful when we have multiple predictors and we're asking different questions. Another piece that I like is looking at predicted scores and comparing that in terms of what we would get from a null model, that is a model with no predictors. The predicted score table we get here is produced by the code above, which you'll get to play with a little bit in the exercises. But one thing that is a little bit strange is how it's laid out. Across the top, it has response listed here as no and yes, and predicted on the side. We're predicted to be a 0, which would mean no. Predicted to be a 1, which would mean yes. I wish it wrote it out like that, but it doesn't. The top and the bottom, the top left and bottom right diagonals correspond to cases that were correctly predicted. For example, we predicted 44 people to be no who actually were no. Remember, response represents what they actually were. Similarly, for yes, we predicted 69 people to be yes, and 69 of those people were yes. The other people are incorrectly predicted. The no's that correspond with the ones, those were people who were predicted to be yes, but were actually no. And then the 7 people who correspond to the 0 yes combination, those people were predicted to be no's, and they actually were in the yes category. What's useful here is comparing this, is first calculating the percent that we actually got correct. That's just 49 plus 69 over the total number of people. So we got about 68.9% correctly classified. One thing that is useful here is not looking at that and saying, wow, 69% is good. It's not necessarily good. It all depends on what sort of baseline we're looking at. For example, if we had a situation where 90% of people said yes, we could simply predict that everybody said yes without knowing anything else, without having any predictors, and we'd be right 90% of the time. But that's not really useful. That's just giving us the baseline prediction. So what we can do here is we can calculate the people, we can calculate basically which category is more common, and then ask, okay, well, what would happen if I just predicted everybody right? How many would I get correct? We can see that the response no has 88 total, where the response yes has 76 total. So we could predict everybody to be a no and get 88 out of the total right. That corresponds to about 54%. So when we're talking about these predicted scores and how many we got right, we always want to compare that to the baseline, because that baseline will make a big difference in terms of how we interpret this. We had almost 15%, almost 15% more, or almost, we were better by 15% here just by knowing whether they had a physician's recommendation. So that's a useful statistic to look at, and helps to give a little bit of better context in terms of how good the prediction is. All right, in terms of interpretation, pretty straightforward. Those participants with a physician's recommendation were more likely to get screened. Generally, I would report the log B, that's the APA style piece for this, of 9.8. My apologies, the slides are going nuts. All right, again, I noted a small error on my slides. There's nothing like giving your presentation to actually find errors. Notice here the APA style, and I changed this from a few seconds ago. The correct notation here is EXP-B. That's the exponentiated B. That means the odds, 9.86. And then I've got the confidence interval listed there, going from 4.3 to 25 and change. Later on, in terms of presentation, we'll add model fit statistics. Those would usually be here. I don't have them in this case because model fit statistics are redundant in these single predictor models, not particularly useful. So we'll see how to present those later. All right, our next set of slides is going to focus on multiple predictors.